Yeah, welcome everyone. Today I will talk about marine acoustic classification on supervised semantic segmentation of Echosounder data using convolutional neural networks. This is based on a paper written by the Norwegian Computing Center in collaboration with the Institute of Marine Research and is part of the COGMA project. First, a bit of motivation. Each year, the Institute of Marine Research collects large amounts of data from the ocean using Echosounder technology, which you can see to the left here. These data are classified into fish species, and the pipeline continues. This is used for stock assessment models to monitor the stock abundance over time, which again is used as advice for determining fishing quotas for commercial fishing, and sort of the overarching goal is to maintain sustainable fish stocks in the oceans. Okay, but the focus of this talk is the acoustic classification step using machine learning. And first, a bit about the data. The data can be visualized like this, where you see the yellow line in the bottom is the seabed, and on top you see the surface, and in the middle is the water containing schools of fish. And these are large groups of fish swimming together. And the vertical axis is depth, and the horizontal axis is distance traveled by the ship. So the ship which records this data travels at a constant speed, and every second it emits a short pulse of sound, and the sound propagates down through the water and is partially reflected by objects such as fish and the seabed. And this signal is then recorded by the ship, and the time delay is converted into depth. So for each pulse the ship emits, you get one column, like one slice of data. And when they then concatenate all these slices of data, you can visualize the data like this. Now the ship transmits 4 pulses at distinct frequencies. So this gives us 4 corresponding image channels, where what you see here is one of the channels. Okay. So onto the acoustic classification step. The task is simply to classify each pixel as either background or a particular species of fish. Now, the traditional way this is done today is a manual process done by domain experts. This is time consuming, and I believe sometimes can be tedious work, and it's also subjective. And the main steps, a bit simplified, is to first identify each school and then analyze the relative response. That is to look at the reflected energy for each of the 4 frequency channels, which then can be used to classify the species. Now, in our work, we wanted to automate this process to support the manual annotation process. So we have annotated image data, and we're doing supervised learning. And we're using the unit-based architecture to perform semantic segmentation, where the input and output to the network is a 256 by 256 pixel patch, which is illustrated by these white rectangles. So the data we've been using is from a sand eel survey. That means that the primary target for annotation is this little fish called sand eel. so we have three classes: sand eel, other species, and background. And here's an example. On top, you see one of the input channels, and then the annotations, and below the predictions made by the unit on a test set example. And visually, the predictions correspond fairly well to the annotations in this example. Now, I want to draw your attention to the highlighted region to the right, where you can see that the annotation is a bounding box. And bounding boxes are actually the dominant type of annotations in this data set. And that is for a good reason. It's quite quick to make rather than these wiggly curves needed for perfect semantic segmentation. And these annotations are intended for integration and not machine learning. And by that, I mean how the Institute of Marine Research uses these annotations in the downstream pipe. And what they use the annotations for is to, they use it as an integration mask over the acoustic data to estimate the amount of fish. Because when you sum up the pixel values in the acoustic data inside this annotation box, you get a value which is proportional to the amount of fish in the school. And then if you include some extra pixels outside, which has value very close to 0, it doesn't really affect the estimate. But we would like this to be a bit more machine learning friendly to be able to use this in a fully supervised setting. So what we do is that we make these refined annotations, which we use for training. So we apply thresholding on the original annotations based on the acoustic data. And we also apply some morphological erosion. And the result is this refined annotations you see below, where the yellow pixels are ignored by the network during training. So that means that loss is not backpropagated from these pixels. A bit more on annotation quality. This data are from the sand eel surveys. That means that the sand eel is the primary target. And other species are more sporadically annotated. And also there are additional species which are not annotated at all. And here you see an example where the model makes a false positive prediction. It believes it is sand eel. Evidently, there is something there in the acoustic data, but it's not annotated. So what we have tried is to frame this as a binary problem instead, to train the model with the positive class being sand eel, and then the negative class being other and background combined. However, we find that training this using 3 classes gives improved model performance. And then a bit about class imbalance. In our data, we mostly see empty water with no fish. So 99% of the pixels belongs to the background class. And recall that the input to the network are these patches. So these 3 rectangles you see here are examples of these. So because of this class imbalance, we want to balance the samples that the network are trained on. So instead of drawing the patches at random, we used balanced sampling, where we fix a portion of the patches containing fish and seabed and background. And we also include patches which contain both fish and seabed at once, because sort of the cardinal error in this field is to classify seabed falsely as fish. And this is because the acoustic reflection from the seabed is extremely strong compared to the reflection from fish, which means that the pixel values from the seabed is very large compared to the fish regions. And if seabed is misclassified as fish, this leads to a excessive estimate of fish when this later is used as an integration mask for abundance estimates. Okay, now on to results and model performance. Due to heavy class imbalance, we evaluate the model with precision recall curves. And as you can see, we show these results per year. We have data from 11 years, and we split the data into training and testing by years. So the years with red curves are used for training, and the years with blue curves are used for testing. And this is because there are large annual variations, such as class distribution, school sizes, biology. Different vessels are used for different years with different instruments and possibly calibration. And the green points you see are used as a benchmark for comparing to our method. This is based on a traditional automated processing software. And we can see that our method performs better than the benchmark for all the test years. There are variations in the performance between years, and the class distribution and the school size affects precision. If the schools, which is the positive class, are fewer or smaller, this will reduce precision. This is exactly what we see here. This is because the false positives becomes more dominant. We do get prediction errors with false positives from the model. Here you see an example with a plankton or bubble layer, and these phenomena are not annotated. So annotations just shows that this is the background class. So this is what our network learns. However, this is a typical mistake that the network makes, giving false positives close to the surface. And we're currently working on improving this with different type of patch sampling, either by sampling more frequently from the upper part of closer to the surface, combined with high intensity regions from the acoustic data. And we're also considering using a purely intensity-based sampling strategy. For future work, we are currently working on implementing additional metadata into the network. So recall that as per now, the network only sees a small patch of data and doesn't really know whether this patch comes from close to the surface or close to the seabed. So adding this information will be sort of additional information to the network and hopefully improve performance and reduce false positives. And we also are planning on including other types of metadata, such as troll catch information. A natural next step will be to apply these segmentation outputs from the network as integration masks, which is one of the inputs to the stock assessments. We're also planning to expand this method to other species, such as the herring surveys, which has quite different type of annotations. So we need to think a bit different. So this work has been part of the COGMA project so far, and this continues. There are also 2 new centers for research-based innovation, which is visual intelligence, as you all know, and CRIMAC. So this method and with the same data will be developed further in these centers. The COGMA project is funded by the Research Council of Norway, where we apply machine learning to different types of marine image data. And this work is based on a paper called Acoustic Classification in Multi-Frequency Echosounder Data using Deep Convolutional Neural Networks. And this is published in the ICIS Journal of Marine Science, and has been a collaboration between the Institute of Marine Research and the Norwegian Computing Center. Then I just want to say thank you very much for your attention.